specimen is already in here. I've bolted it to the top. So come around here so that you can see this. I'm standing on the ladder in an unsafe way. So there are 2 bolts on the top that hold it in. Okay, so if I undo this, there's 2 bolts on the top, one on top of the other. So I did this before a class to save us a little time. Okay, so you see the specimen dropping down. So before a class, I put this in. And the bolts up here follow the left-hand rule. So typically righty-tighty, lefty-loosey. But for some reason, these follow the left-hand rule. And now I'm putting the bolts on here like so. Okay, and then there's some bolts on the bottom. See these 2 bolts here? These will be placed on the bottom. So these bolts are going to be on the bottom to keep it in place on the bottom. Okay, so I turned on the controller and it says waiting for Windows, so I have to fire up the software. So take a look at this. Can you zoom in on this? Shortcut to MTestW. So I'm going to double click on this. Okay. You getting that? Okay. So I'm going to wait for the software to open here, MTestW. Okay, transfer in progress. Okay. All right, so what does it tell me to do now? It says turn on the hydraulic pump using the green button. Okay, that'll be this green button. Okay, then it gets really noisy. It says click the use test setup icon. So that should be the 7th icon over. 1, 2, 3, 4, 5, 6, 7. So that'll be this icon right here. Okay, and then I want to float the table. I have to float the table first. So the name of the file is in the checklist. It says go to 0.5 inches. So go to 0.5 inches. That will be right here. So I open up that file, like so. Okay. Okay, it says float the table. Remember from the other day what that means, float the table? Take a look at this here. I want the loading deck to move up by 1/2 inch. Remember this from the other day? Okay, so that's what I'm going to do. So coming back to this, I'm going to press 0 all, and then I'll press play, and I'm going to watch this go up by 0.5 inch. Is it moving up? I should know, my face is right up against it. I forgot to put on my goggles. What if one of those hydraulic lines pops a leak? I'm going to put on my goggles in a minute. I'm running a risk here. I'm running a risk of getting hydraulic fluid in my face. Okay, and I think that's it. So now I'm going to go back here to the 7th icon over, right here, and then I'm going to open up the file that is Poisson's ratio. So I'm looking for the file called Poisson's ratio. Poisson's ratio, where is it? Which one is it? Like I see it there in the upper right-hand corner, but let me make this bigger so that the folks at home can see it. Poisson's ratio right there. So I click open, and now the file has opened. Okay. So this is the file that controls the load increments. Remember I said we're going to stop every 3,000 pounds, remember that? So I set it up so that that would be the case. So if I go up here to test, and then I'll say test setup. Okay, test setup, I'm going to go to servo profile, and if you take a look at this, it tells that I'm stopping at every 3,000 pound increment, and I'll be stopping there for 2 minutes. That's 120 seconds. I wrote all this line of programming. I wrote all this, and it only has so many lines that I can put in, so that's why I changed it from 2,500 to 3,000, because if I try 2,500, then I run out of lines. So all of that is programmed in here. So when I post this video, you'll be able to see this up close. All the lines of programming that I put in there. But all this is good. So I'm going to X out of this. Okay. So where am I on the checklist? Bolt the bottom of the specimen in place. So now I'm going to put the bolts on the bottom. Okay, watch this. On this side you can see it. On this side you probably can't. But this is following the left-hand rule. And I have to move that crosshead up a lot because there's another bolt I have to put on here. So I'm going to move the crosshead up. Wrong way. enough more, a little bit more. You getting this? Okay, so I put that bolt on, now I'll put this bolt on. I gotta move it up just a little more. I think that should do it. When we're done, I'll take out the specimen so you can photograph it. Okay, there, I think it's nice and tight. Got both bolts in on the bottom. See that? So now the specimen is completely in place. Okay, it says verify that the switching and balancing unit is set to 4 arms. So take a look down here. 4 arm, I'm going to turn it on. Turn on the BLH strain indicator. Okay, I did that. And the switching and balancing unit, that 5th thing, turn it to channel 1, which it is. It is. Turn the strain measurement wheel on the side of the strain indicator so that it reads 2500 in the window. So I see 2500 in the window right now. And I want the black needle and the balancing meter to be in the null position. I can control that with this knob. Okay, so by turning this knob, I can control the little black needle in there. See it moving? I want the window to read 2500 and the little black needle to be in the null position. There you go, that's channel 1. Now I'm going to switch this over to channel 2 using the channel selector switch. It's a little black needle in the middle. And does it read 2500? It better. I can change it using this knob. See the little black needle moving? So I can actually control it through the switching and balancing unit. Okay, so where am I on the checklist? Everything good here? Switching and balancing. Okay, so I guess we're ready to start the test. You got a place to record this. I got my worksheet ready. So now I'm going to start this test. What is the date today? 16th. Okay, so 7/16/25. Okay, watch this. So now I'm going to start the test. First I'm going to zero it out. I don't want a 230 pound preload. So watch this. Okay, you got this here? I'm going to press 0 all and then I'll press play. Now watch this. It's going to pick up load and it's going to stop at 3000. All by itself, it's going to stop at 3000 and it's going to sit there for 2 minutes. Okay, so for the first line, you put 2500 on both channels, 2500. Okay, see how it stopped at 3000? So now I'm going to take a channel 1 reading by turning this knob to 1, turn the knob to 1, and then turn the knob on the strain measurement wheel so the little black needle is in the null position. And in the window, I read 2715. So that's at 3,000 pounds, 2715. And then I'm going to switch this knob to channel 2, and then I've got to rebalance the Wheatstone bridge by turning the strain measurement wheel. And I'm reading 2440 in the window right there. 2440. How is that? Okay, now watch what happens after 2 minutes passes. Watch what happens after 2 minutes pass. Okay. Who wants to take the next strain reading? And if you're okay with being filmed, you already volunteered today. Okay. Any new people want to volunteer? You have to be willing to get filmed. You're willing to get filmed? Okay. Are you still filming? Okay. Is the 2 minutes up yet? This is telling you that the x-axis is time. So after 2 minutes, it'll start picking up load again. I'm going to change this to channel 1. And when it starts picking up load and goes to 6,000, he's going to come up and take a reading. So just give it 2 minutes. We're almost there. 2 minutes is about here. So I don't even have to do anything. It's like on autopilot. A little bit longer. So we'll just wait here, hang out till it starts picking up load again. See how it stopped at 3,000? Okay, now in just a minute, actually less than a minute, about here where my finger is, it'll start picking up load and it'll stop at 6,000. Okay, now it's picking up load. Wait till it gets to 6,000. And then, sir, you can take a reading on channel 1. I changed the channel selector switch to 1. So wait till it gets to 6,000, which is right here, and you'll see a plateau. Is that 6,000? Actually, it's right here. Okay, so now, sir, it's at 6,000, so can you take a reading for me? And make sure you get him taking a reading here.
But
Big
moving-
wheel, big one on the side. The other direction. Actually, you're right the first time. What a fool I am. Yeah, keep going. See it moving? So now it's in the null position. What number do you see there?
2920.
2920, thank you.
What channel?
That's channel 1.
Okay, now.
We don't want to dilly-dally too long because we only have 2 minutes. So now I'm going to change this to channel 2. Who wants to take a channel 2 reading? And you have to be okay with getting filmed. You're okay with being filmed? Okay, so make sure you get him doing it. And then after that, I'll get a new camera person in here. Okay, so sir, please take a reading. Big knob on the side.
Up or down?
Down. Fast. A lot. Okay, there it goes. Now in the middle, what are you getting?
2390.
2390, thank you. Okay, so now we are, we're picking up load. Next up is 9,000 pounds. I'm going to change this back to channel 1. Okay, we're at 9,000. Who will take a strain reading and doesn't mind getting filmed? Sir, you can do it? Okay, so take a strain reading, please, at channel 1. Yeah, you got it. What does it say in the window?
3130.
What is that?
3130.
3130, thank you. Okay, now I'm going to change this channel selector to channel 2. Who wants to take a channel 2 reading? Okay, you don't mind getting filmed? Okay, so sir, please take a channel 2 reading. See, we're at 9,000. See how it leveled off? What do you see in the window?
It's in between.
Okay, so between what? 10 and
50
20?
and 40.
50 and 40? Okay.
No, 30 and 40.
Okay, so it's 2335, 2335. Okay, so have we used up the entire 2 minutes? Okay, if we're in a hurry and we don't want to wait 2 minutes, okay, get a close-up of this. I'm going to go to this icon right here, which is next servo segment. So when I click on that, then it'll pick up load. I don't have to wait for the 2 minutes. Okay, thank you. So we're going to wait until it gets to 12,000. And then I'll need someone to take a channel 1 reading. Who doesn't mind getting filmed? You don't mind getting filmed? Okay, so he's going to take a reading at 12,000. It looks like we're at 12,000. See, that's what the control panel was telling me. So, sir, if you could take a reading for me here.
It's 3330.
Okay, 3330. Thank you. 3330. You notice how the numbers are getting bigger in the channel 1 direction, but they're getting smaller in the channel 2 direction. You notice that? Okay, channel 2. Who wants to take a channel 2 reading and doesn't mind getting filmed? Okay, sir, can you do it? So I switched the knob to channel 2. Everything good here?
Where's the dash?
You were going right, yeah, correct. You're correct the first time. There it goes.
2280.
2280, thank you. 2280. Okay, next up, 15,000. All this yelling is making me thirsty. You still filming here? Who will take the readings, a reading, at 15,000 and doesn't mind getting filmed? You don't mind getting filmed? Okay. So I'm going to change this back to channel 1. If I'm in a hurry, I'll just click on next servo segment. Or if I press F10, if I press F10, that'll also do it. So let's wait until I get up to 15,000. So I click on F10 or next servo segment if I'm in a hurry, if I don't want to wait 2 minutes. But when I programmed this, I figured that 2 minutes was enough. I could have programmed it for 3 minutes, but that would have been too long. Okay, so we're at 15,000. Sir, can you take a reading? Who was that who volunteered? Oh, there he is. Okay, so I'm on channel 1.
the same.
Yeah, the biggest knob there. Yeah, I think, yeah, you're right. Correct direction. Yeah, keep going. Okay, there it goes. Okay, it says what?
3540.
3540, thank you. Who wants to take a channel 2 reading and doesn't mind getting filmed? Sir, you'll do it? Okay. I switched the channel selector to channel 2. I need like a stopwatch here to tell me how much time has passed before it picks up loading it.
2230.
2230, thanks. In a moment, it's going to start dropping back to 12,000. I changed the channel selector back to channel 1. Anyone want to take a channel 1 reading? Who doesn't mind getting filmed? Sir, you don't mind getting filmed? Okay. Okay, now it's dropping back down. You see it dropping back down? So wait till it gets to 12,000. And then we will take a channel 1 reading. And it'll settle at about 12,000. See how it kind of settles at 12,000 approximately? Okay, so I noticed there's a little bit of a problem at 12,000. It kind of bounces around a little bit. I can kind of see it in the graph, but I think it's settled down. Try 3365. 3365. Channel 1. And then while I'm here anyway, I'll take a channel 2 reading. At 2275. 2275. Okay, and I wrote down that it's more like 12,375, not really 12,000. Okay, so the next stop will be, should be 9,000. Okay, now it's dropping already. Okay, who wants to take a reading at 9,000? Sir, you'll do it? And you don't mind getting filmed, I hope. Okay, so I changed the channel selector to 1. Okay, so, sir, I think it's ready. Now we're about 9,000. Okay, yeah, what did it say there?
3130.
3130, thank you. And that agrees with what we had on the way up. Okay, channel 2. Who wants to take a channel 2 reading? It doesn't mind getting filmed. Sir, can you do it? $23.30, thank you. Okay, so now I'm waiting for us to get back to, what is it, 6,000? 6,000. How much time do we have? See that? The x-axis is time, the y-axis is load. So the next stop will be 6,000. I'm waiting for the 2 minutes to pass, and then we'll see the load drop to 6,000. I hope. Sometimes there's a glitch in the software and something weird happens, but I think this should be okay. I'm going to change this back to channel 1 on the front of the switching and balancing unit. Okay, see, it's dropping back down. See this? Anyone want to take a channel 1 reading? Have you volunteered, sir? Okay, so sir, can you do it? Do you mind getting filmed? You do mind getting filmed?
Maybe.
Okay, well, to do this, you have to be willing to get filmed. I'm going to change this to channel 1. Okay, I'll try not to get your face in there. Okay, your face isn't in it.
2920.
2920, thanks. 2920. See how I have to multitask here? I'm doing a bunch of things at once. Now change this to channel 2. Okay, channel 2. Where are we? Are we still at 6,000? We're still at 6,000, aren't we? Are we still there? Yeah, still at 6,000. So a channel 2 reading. To do my job, you have to be kind of a jack of all trades. kind of doing a bunch of different things at once. 2380, so 2380. Okay, what's the next stop? 3000? If I'm in a hurry, I can just click on next servo segment, or F10. So I clicked on next servo segment, we'll see it drop back down. So now it's going to drop down to 3000. I hope. Sometimes there's a glitch and it stops at some other load, but it should be 3000. Did it stop at 3000? I see that the graph is kind of leveling off there. Yeah, about 3,000, good enough for government work. 29 something. I'm going to change this back to channel 1, and I'm going to take a channel 1 reading. So channel 1 reading. If you didn't get a chance to volunteer today, there'll be plenty of other opportunities. So I am reading in the window 2715. 2715. And now I'll take a channel 2 reading. Okay, now I'm going to come over here and I'm going to take a reading for channel 2. 2430. 2430 for channel 2. 2430. What's the next stop? 0. Yep, 0. Yeah. Okay, so where are we now? We're not back down to 0 yet, are we? So when we wait for the 2 minutes, after the 2 minutes has passed, then the load will drop back down to 0. I'm going to change the channel selector knob to 1, and I'm going to take a reading at 0. Sometimes there's a little glitch in the software and it stops. Instead of 3,000, I get like 4,000. But it seems to be working today. Okay, did it get back? I'll be darned. Look at this. Negative 199. We'll consider that 0. So let's see what we have here for the measurement. So 2,500 for channel 1. Now I'm going to change this to channel 2. Channel 2, and then I'm going to take a reading. 2,500. It's about 2,500. So 25. Okay, so now I'm going to remove the bottom bolts. I'll do it one-handed. Okay, I'm removing the bottom bolts. Remove the bolts on the bottom. Okay, like so. Okay, see, I took out the bottom bolts. See that? Exit this. Okay, so I'll go up here to test. And then exit. Okay, and what happens to the hydraulic pump? Shuts off, and then I'm going to shut off the machine on the, don't leave yet. I'm going to shut off the machine over here on the right, the lever over here on the right, that shuts off the hydraulic pump, like so. And then I'll shut off the controller in just a moment. I'm going to shut off the controller. So that's how you do this lab. And now I'm going to shut off the strain indicator. You'll want to shut off the switching and balancing unit. Here's a worksheet that I made available to you so as to allow you to calculate all the relevant data. So the channel 1 results that we got from this activity, 2500. All you're doing here is typing in the numbers that are from the worksheet. So if I type something incorrectly, maybe you could let me know in the comments. 12,000 pounds. I think I was saying 12,375. I don't know that it would make that big a difference. Notice that I programmed this spreadsheet so that the load is repeated over here in column I. And when I change this to 12,375, it updates over here as well. So at 12,375, I was getting 3365. Maybe some of these other loads are a little bit off also. I was trying to multitask while I was doing this lab activity, so I don't know, maybe 9,000 was actually 9,100. I wasn't really paying attention. But the 12,000, I did happen to notice that that was a little bit more than 12,000. I don't know that it will make that big a difference, but nevertheless, at the 9,3130. So all I'm doing here is typing in the numbers that were collected in the materials lab. And then the cross-sectional area for this. I told you what the cross-sectional area for this was, didn't I? Uh, 0.9575. 0.9575, and then the date, that was July 16th, 2025. Okay, it tells me what day of the week it was, Wednesday. Okay, now channel 2 I'm going to put over here. See the column that I made kind of in a light brown there, the light brown column, or peach color, or whatever that is. So 2500. So I'm just typing in the numbers. Oops, 2330. 2380. Where am I? 2430. And then I got back to 2500. Okay, so now I typed in all the data. So column C is just column B divided by 2. Now, why am I dividing by 2? The reason I divide by 2 is because there were 2 gauges in the longitudinal direction. If you remember from earlier in the video, each side of the specimen had 2 strain gauges. Channel 1 was reading the strain gauge in the longitudinal direction, but there were 2 strain gauges in the longitudinal direction. There was one on the front and one on the back, and the strain indicator is actually reading both of them simultaneously. That means that I want to divide by 2 so that I can be getting a reading from only one gauge at a time. Did I say that correctly? Maybe. But I'm just dividing by 2 because the strain indicator is reading 2 gauges simultaneously. I want to know what each gauge would get individually if I only had one gauge in the longitudinal direction. And the strain indicator is adding the results together. I don't really want that. I want what the longitudinal strain gauge is if I were only using one gauge. Okay, so I'm dividing all of the numbers in column B, B as in Bravo, divide all those by 2. And then I can copy this down. So copy and then paste here. I think that's going to mess up my line here. It messes up my line, but I can go back and fix that later. Maybe I can fix it now. I want a thick bottom border. Did that do it? That does it. Oh, I'm gonna mess up the border here too. Okay, now I fixed the border. Okay, similarly for channel 2. So channel 2 is measuring strain in the transverse direction. That's perpendicular to the longitudinal axis of the bar. So it's the same idea. I'm going to divide column D, D as in delta. Divide that by 2. So what I'm calculating here in column E is what the strain would be if I only had one gauge. See, the strain indicator is measuring both gauges at once. There's one transverse gauge on the front and one on the back. But I don't want to be double dipping. So I only want the transverse strain, not double the transverse strain. Okay, how is that? Did I do that correctly? So far, so good. Okay, so the longitudinal strain, this is epsilon subscript L, that's longitudinal strain. So you realize that when I get a number here in column C, that's not the strain. The strain would be the difference between whatever the number is and whatever the initial datum reading was. So obviously when there was no load on the specimen, that means no strain. No longitudinal strain, no transverse strain. So those are going to be zeros. But for column F3, this is equal to the reading in column C, row 3, and then I have to subtract off what the initial reading is. And now I'm going to keep using this formula, so I have to put dollar signs around this, because when I copy this formula, I have to keep referring back to C2.
Okay, so 107.5. So what that is 1,357.5 minus 1,250. That's what this number is. And then similarly for the transverse direction. So this is equal to the strain from channel 2 as measured by the strain indicator, or at least half of that. That's cell E3. So E3 minus what the initial reading was. So that'll be E2 like this. And then when I copy this formula, I'm going to have to keep referring back to E2, so I'll put dollar signs around this. Negative 30. I would expect it to be negative because the specimen is getting skinnier in that direction. So now all I do is copy this formula. Copy this down like this. Okay, and I've got my longitudinal strains. Be careful, this is micro inch per inch. So when it says 415, that doesn't actually mean 415 inches per inch. It's 415 micro inches per inch. So it's 415 times 10 to the negative 6. These are very tiny quantities. Okay, and then I'm going to copy this cell down like so. And there you have it. But now all the cell borders are messed up, so I have to fix that. And when I submit this for my lab report, I want it to be very professional looking. Okay, so there you have it. So now the second part of this table, over here if you move over, the reason I split this up is because when you print it onto paper, if I have it all as one table, it might not print out very good. So the reason that I split it here, you notice the column H is just blank. So I find that when I split this big spreadsheet up into two different parts, when I go to print it, it will turn out a lot nicer. It'll look a lot nicer when I go to print it. Okay, so the sigma A, what is stress? That's load divided by cross-sectional area. So the cross-sectional area, I think, is 0.9575. That's in B14. Okay, so obviously if there's no load on the specimen, then there's no stress. So you can just put a 0 there. Okay, so for 3,000 pounds, this is equal to the load, which is 3,000. And then divide that by the cross-sectional area. The cross-sectional area is right here. And then I'm going to have to keep referring back to this formula when I copy and paste. So I'm going to put dollar signs here. Okay, like that. So that's my stress. And I should probably show a reasonable number of decimal places. So I go up here to format, and then a number, or pardon me, format cells. Okay, and then number, maybe 3 places, 4 places. Okay, that's good enough. Okay, so that's PSI. So now copy this down, like so. Okay, and I wind up with this. How do you like that? So these are stresses. Okay, so there you have it. Those are the stresses in PSI. Does that seem reasonable? Okay, moving on down. That's the Greek letter nu. That's Poisson's ratio. What is Poisson's ratio? It's transverse divided by longitudinal. Some books put a negative sign in front of the epsilon sub t because you notice that if I divide a transverse strain by longitudinal, it'll be negative. Some books will get rid of that negative by putting a negative into the formula. 2 negatives make a positive. So I think I'm going to program it that way. I probably should have said that here. Maybe if I put a negative in here, it'll be clear what I actually mean. Okay, you can barely see it in there. Negative epsilon sub t divided by epsilon sub L. Okay, not applicable if there's 0 load, so forget about that. Okay, now it's going to get interesting because at 3,000 pounds, Poisson's ratio will be the transverse divided by the longitudinal strain. So that'll be this cell divided by this cell. Okay, and I wind up with this number. You know what? I forgot to multiply by -1. I don't want that negative in there, so I'll say -1 times all this. See me typing in all the coding up here? 7, 9, or 1? How many decimal places do you want? 4 is okay, I guess. Okay, and then copy this. Okay, and I'm getting some kind of error message down here at the bottom. You can't divide by 0. Huh. What should I put there? I don't need anything. Nothing's happening at 0. Nothing really relevant is happening at 0. So Poisson's ratio, I guess this is kind of misleading where I say 0 here. Maybe just a dash, meaning that it doesn't apply. We'll put a dash there. Okay, I think that'll work. And then I'm going to fix the cell border. Okay, so what do I see from this? You see that Poisson's ratio here. Poisson's ratio is here. Is about 0.27. Now some of these numbers seem a little weird. 0.32. 0.32, that seems a little high, but notice that most of them are about in the 0.26, 0.27 range. We're using a very old piece of equipment, so I'm not expecting the level of accuracy that you would expect if we were going to send this data to Northrop Grumman or to Boeing. So as long as we're somewhat in the neighborhood of 0.26, 0.27, 0.28, it's certainly good enough for government work. So you're doing this correctly if all of these numbers are about in the same ballpark. This 0.33 seems a little weird, but all of these others seem good enough for government work. If you're getting some weird number like 0.9 or 0.87, then you're probably doing something wrong. Probably something very wrong. But this is an anomaly down here. Okay, now what is Young's modulus? Modulus of elasticity, named after Thomas Young, a British eye doctor who lived in the olden days. Okay, well, Young's modulus at 0 pounds, I don't care, so I can just put a dash there. Okay, so E, that's, well, it's telling you here, it says it's stress divided by longitudinal strain. So this is equal to stress, which is right here, and then divide that by longitudinal strain, which is over here. Okay, like this. 29. What did I do wrong? What did I do wrong? 29? That doesn't make any sense. So try this again. Now J3, that's PSI, and then divide by F3, but be careful, that's micro inches. So here's what I did wrong. This is F3 times 10 to the negative 6, because it's a micro inch. Micro inch per inch. So let me see if this is more reasonable. Okay, well, what have we got here? 29,145,668. If I read that incorrect, you can write a nasty note to me in the comments section. Okay, so about 29 million. So now I'm going to copy this. Okay, should I include that last cell? Okay, well, it's giving me an error message, so just get rid of it. Okay, how is that? And now I'm going to fix the cell border here. Okay, yeah, satisfied with that? Okay, now what do I notice about the modulus of elasticity? They're all about 30 million-ish, 29 million-ish. Yeah, so that's about what I would expect for steel. I think that specimen might have been some kind of steel. Might have been. It looked like it, and it felt like it. And it was sure heavy when I put it into the machine. So I think it very likely was steel. And at 29 million, 30 million, that's typically what I would expect for the modulus of elasticity. So these seem like reasonable numbers. How do you like that? What is shear modulus G? What is shear modulus G? What is that? Shear modulus? Okay, there's an equation for this. So the equation for this is Young's modulus E divided by 2 times 1 plus Poisson's ratio. So 2 times 1 plus Poisson's ratio, which is in column K. K is in kilo. And you see how I'm typing in the coding here? Make sure you put parentheses there. So what did I just do? Look at the coding up here. So it's L3, which is Young's modulus, and then divided by 2 times 1 plus Poisson's ratio. I think that's correct. So what am I getting here? 11,393,306. Okay, so there you go. And now I'm going to copy this. Before I copy it, I think I'm good. No, before I copy it, nothing. Everything is good here. Okay, so now copy this down. Okay, I don't care what's happening at 0, so I'll only copy it down to 3,000 pounds. And here's what I get. And I forgot to fix the cell border down here. So I want to make this really nice and professional looking. So the formula for shear modulus is Young's modulus divided by the product of 2 and 1 plus Poisson's ratio. And so you can look in your solid mechanics textbook if you didn't catch what I just said. Okay, now what do these numbers look like? Does this look reasonable? 11 million something? I'm getting in the high 11 millions. The high 11 millions. How do you like that? Now, I'm not a materials scientist, but I hear that for most steel, shear modulus should be about 0.4 times Young's modulus. So if I take, 30 million, let's say, 30 million, that's typically the textbook value for Young's modulus as far as steel goes. If you take 0.4 times 30 million, you get 12 million. So does that make sense? What is 0.4 times 29 million? That's about 11,600,000. So these numbers certainly seem reasonable. If they're drastically different from each other, then you're doing something wrong. But these are all in the high 11 millions, so they seem reasonable. This last one seems a little bizarre, but we're not sending this data to Northrop Grumman or Boeing, so it's not that important. And then lastly, E, little e there, be careful, that's not Euler's number. Don't say 2.72. That's not what I'm talking about. This is called dilatation. So the formula for dilatation, it's the change in volume divided by the original volume. I never did bother measuring the volume of this specimen. Does the volume change? Well, the bar that we tested, as it's being subjected to tension, there's molecules, there's little particles that make up the bar, and those little particles that make up the bar, the specimen, get pulled a little bit farther apart. So therefore, I would expect the volume to get a little bit bigger as it's being subjected to tension. So dilatation is change in volume divided by original volume. All that is stress, sigma sub A, divided by Young's modulus times the quantity 1 minus 2 times Poisson's ratio. Okay, so what am I saying here? Okay, here's my whiteboard. You probably missed what I just said. So dilatation E is equal to change in volume divided by original volume. And that's equal to sigma sub A divided by Young's modulus E times 1 minus 2 times Poisson's ratio. So this is the formula. Okay, this is the formula right here that I'm about to program in. So we'll watch this. Okay, where am I? Okay, so I'll put this in. This is equal to, extra parentheses never hurts. So a sigma A, which is this, divided by E, which is this. Everything good so far? Okay, so sigma A divided by E times 1 minus 2 times Poisson's ratio, which is this. Okay, and then close parentheses like this. I think I typed that correctly. I'm expecting a really small number. And now this number is going to be different because it's going to change based on the amount of loading because the stress is changing. So as you can see, this depends on sigma A. So the sigma A is getting bigger. Did I type this in properly? So J3 divided by L3, that's sigma A divided by E, and then times 1 minus 2 times Poisson's ratio. Okay, if I blew it, you can write a note to me in the comments. Okay, so copy this down like so. I don't care what's happening at 0. Okay, like that. Wow. Okay, maybe I could have a uniform number of decimal places here. How many decimal places do you want? 2? No, I don't want that. 6? Huh. Okay, well, whatever. Okay, let me fix the cell borders here. Okay, fix that, and then I want to put some dashes if the data is irrelevant. Okay, so I think that's it. So when I print this out, it's going to print out really nice. So now let's print it. So I'm going to go up here. I should probably save it first. Okay, well, I'm going to save. Well, I'll imagine that I save it. So now I'm going to print it on my home computer here. Now, this is how I want it to be printed. You see how this will come out very nicely on 2 different pages. So you see the first page. The first page, it's got the load, it's got channel 1, channel 2, that's the raw data, the original data. And I have the necessary strains here. And then on page 2, I've got the load again. And then the stress, Poisson's ratio, Young's modulus, shear modulus, dilatation. So this is what I would call a very professional looking table. So when you print this out, make sure that, for example, the epsilon sub t column isn't pushed onto the next page. So you have to adjust your scaling so that it turns out looking like this. Okay, so I don't know what your setting will be, but make sure you adjust your settings so that it prints out like this. This is how I want to see it. Okay, now I'm going to go back and remember to save it. So there you have it. That's how you put together this wonderful data table, how the numbers that we collected in the lab translate over to some real life numbers here. We figured out what Young's modulus is, what shear modulus is. We know about the strains in both the longitudinal and the transverse directions. So this is pretty good considering that we're using very old equipment. But nevertheless, the results turned out to be pretty good. So there you have it. And please stick around for the field trip that we're about to take. I'm going to take you to the Big 4 Bridge in Louisville, Kentucky.